No.
Okay. So we're going to talk about BCD counters. BCD stands for binary coded decimal. And you know what a counter is? We just saw the previous handout where we're counting from 000 to 111, which is 0 to 7. And then by rearranging the clocks and going to the Q naughts, we can count down from 111 to 000, which is counting from 7 down to 0. Okay. So these counters, basically, we're going to learn how to count to any number we want. This one here, this first one, we're going to learn how to count to 10. How do we count to 10? How many bits do we need to count to 10? With 3 bits, we can count from 000 to 111. But what is 111? A maximum of?
7.
7. How do we count to 10? What do we need? Do we need a
3
fourth?
bits. 3 bits.
But
4 bits. 4 bits. 4 bits.
4 bits.
Yeah.
So 4 bits can count all the way to from 000 to 111. But 111 is 15. So what do we do if we just want to count 10 numbers? I don't want to count 16 numbers. I want to count 10. What do I do?
You need to reset it.
After 10?
You reset, okay?
Reset.
Basically, we're going to use the clears of the JK flip-flops. But there's circuitry involved using gates, okay? So it says here, till now we have seen counters in mod n, where n was a potency of 2. So basically we saw mod 4, we saw mod 8. We didn't see a mod 16, but you can see where a mod 16 would reset itself as well, okay? So what we need to do is we need, in this example here, where we're going to build a mod 10, what we have to do is have a truth table. So remember that when you do build this truth table, don't start counting this as row 1, because what is the value of 0, 0, 0, 0? It's a 0. So I would start off with this. Write down all the numbers here, 0, 1, 2, 3, all the way down. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, right? So if we have 4 bits, it's 16, we count 16 numbers, hexadecimal, from 0 to 15. But we just want to count 10 numbers from 0 to 9, right? Based on what we're saying here, I want to build a mod 10. So what if I build a mod 10? Well, you're going to need this truth table. From that truth table, what's going to be very, very important. Do you see this guy right over here? Right here. Do you see that guy that's highlighted? Where did I highlight it? I highlighted it on the number 10. So if I want to build a mod 10, I go to 10, which is 1, 0, 1, 0, and I put a 1 here. Anything above this one here is a 0, okay? Because I still have to build a Karnaugh map after, okay? All this is 0, anything above it, okay? So I'm also gonna here, I'm gonna envelope it, encapsulate it, isolate it, quarantine will be a better word these days, quarantine it, okay? Anything above it is 0. Anything below it is an X, which is something we haven't seen before, okay? So far, so good. These are the steps. You have a truth table, you want to count till 10, you go to 10, you write a 1. Everything below, anything above that, excuse me, is 0, anything below that is an X. So what do we do with this now? Well, do you remember when we started with truth tables and we started saying whenever we had a 1, we have to extract an equation? Same thing here, okay? Are we ready to go to the next page? So on the next page, we have a Karnaugh table. I've taken the liberty to fill it out for you. Excuse me. But I didn't fill everything in. So 0, 0, 0, 1, 1, 1, 1, 0. Jinja Ninja.
Yes, sir.
Jinja Ninja, don't forget, this is reverse, say 1, 1, 1, 0.
Yeah.
Okay. So now, another thing you have to kind of get used to is we need equations with Q's because we have to know where to hook things up. Now, which one is A, B, C, and D as opposed to these? If you want, on the side, make yourself a mini mind map, not mind map, a Karnaugh map, I should say. And how do we number this, or how do we identify before? We said this was A, B, C, and D. So just do the same thing. Q4 is A. We're not going to use it, but it's just so that for now you have a little bit of a way of understanding it, okay? Remember that Q1 is D. If we go back to the previous handout here, have a look. Q1 is D. I always remember that. Q1D, Q1D, Q1D. So Q1 is D. And the rest is fairly easy. Okay? 2, 3, 4, the C, B, and A. So what are we going to write down here? Same as before, where we had A, B, and all that. A, B, C, D. But we're going to write down Q4, Q3. Okay? But of course, there are values of 0, so they're going to be knots. Okay? So can you fill the rest of this in, please? Fill the rest in. So the only thing that's different here as opposed to the other Karnaugh maps that we've done or other Karnaugh tables is the fact we have x's. Now it's not imperative that every x is taken care of. The important one is the 1, but you want to make the biggest group possible with the 1 and the x's. So meaning that I could do just this, but that will leave me with a larger equation and a larger reset circuit. So ideally, what those x's are good for is to, I can make a group of 2 here, I can make a group of 2 here, but ideally, what do you guys see in terms of grouping? What would be the best group with that 1? 4. You can make one group of 4 right over here. Okay?
X's represent what number?
X does not represent a number. It basically represents anything underneath the reset. It just means that this counter will not get beyond 10. It won't get to 11, 12, 13, 14, 15. That's why there's an X. Okay, it won't get there. But it will get to everything before it, 0 through 9. So what happens with these 2 here? What happens with the 2 X's? These 2 X's here are not important. Now I've encircled them. Hopefully that doesn't mislead you because I'm going to write down here not important. In other words, forget it. It doesn't matter. Okay? What's important is what's in blue here. And what's in blue here, you have to extract an equation. So what equation do I get here? I'm going to write it down right over here. So the blue group. Well, between these 2 rows, this row and this row, what changes? Q3 changes. So I'm left with Q4. Between this column and this column here, what cancels?
Q1.
Q1 and left with times Q2. That is my reset equation. I'm going to use this reset equation to reset at 10 so that I'm only going to have numbers going from 0 to 9, and then when it gets to 10, it's actually going to reset. Okay? So it says here, draw the reset circuit. Now, the only other thing here is that if I were to draw a JK here, right? So I need a J, I need a K. You're going to need to do this, by the way. eventually and draw all this. I'm going to have a preset and clear an inverter here. Okay. Remember the clear, which is at the bottom. What does that little dot mean?
Invert.
This guy here means that it's negative logic. What do I need here to clear the Q so that it resets to 0? I need a 0, so it resets to 0.
Yeah.
So my reset circuit, which is basically made up of this, the only thing I have to do is I have to make sure that it's a 0. So how do I do that?
Invert.
Invert. So I'm basically going to take this guy here, Q4 multiplied by Q2, which is an AND gate. But the only thing is, it needs to be a 0.
A 0.
So I need to invert. So it's a NAND gate, and then this NAND gate will go to my clear.
Yes.
Okay. Now I've yet to draw the complete circuit, but here it says draw the reset circuit, and that's what this is. This guy here is the reset circuit. So you'll have one input of the NAND gate going to Q4, and the other input is going to go to Q2. Now for reference, where is Q4, Q2? Well, if we go back to the previous handout, I don't have a Q4 because I don't have 4 bits, but it's basically these Qs. It would be Q4, the 4th JK here, and Q2. I have to tap off of those two, okay? By tapping off, I mean I have to bring a wire to Q4 and Q2, okay? So let me recap. If I want to build a mod 10, I come up with a truth table. When I get to 10, I put a 1. Everything above it is a 0. Anything below it is an X. I take all of this, plug it into the Karnaugh. I want to get rid of the 1, but I can get rid of the 1 by making a bigger group with the help of the X's. I do not need to use any X that doesn't fall into a group. My simplified equation is Q4 multiplied by Q2. In reality, what that is an AND gate. But since my clear is reverse logic, in reality, this would be knotted. Okay, it's always going to be knotted because we're using reverse logic gates. Okay?
Excuse me, sir.
Yes.
Here, I have one question. We to the clear to how to say 4 chips clear or the first one?
All 4 at the same time.
To the 4 at the same time, yeah. Okay.
Yes.
Thanks.
No problem. Okay, we're going to draw that. We're going to draw it together. Okay? So what it's saying here, I want you to understand this. We have a 4-bit counter, so we have 4 flip-flops. In this case here, we're looking at 8. We're not going to start all the way from 0, 0, 0. So let's say we get to 8. It's 1, 0, 0, 0. So 1, 0, 0, 0, the 7th segment will display 8. Remember, this is a mod 10. It's going to continue to count 1001. 1001 is what number?
9.
9. And then magically, it's 1010. But if we have 1010, we just built a circuit that taps into Q4 and Q2. When these are both 1, the output of an AND would be 1, and inverted would be a 0. If I put a 0 here, what's going to happen to the gates? To the gates, to the Qs.
Active.
They're all going to go to 0. Okay? I know it's a lot to take in at first, but when Q4 and Q2 are both 1s, when Q4 is a 1, Q2 is 1, which is basically when we get to 10, I'm going to get an active low with my NAND gate, and it's going to clear my circuit. Now, this is the complete mod 10 circuit, but I want you to draw the clear, okay? Well, I don't need you to draw it. I need you to copy what I'm going to draw. How do we integrate this guy here into this drawing here. Okay? So I'll show you. I'm just going to draw the NAND gate going this way here, just so that there's less crossing. So what do I tap off of? Well, first of all, let me just identify this a little bit better. Remember, this is the first flip-flop. Which Q is this guy here? Q1. And Q1 is going to which LED or which input on the decoder? A, B, C, or D? Not even one person knows the answer to this?
D.
D. This guy here will be Q2. Why is it called Q2? Because it's a second flip-flop. Second flip-flop. Now we're going in alphabetical order or reverse order. I will be C. This would be Q3, which is B. And then we have Q4, which is A.
A, yes.
Okay, so remember, how much is this worth? 1, 2, 4, or 8?
This is 1.
This guy here is worth?
This is 2.
This guy here is worth?
4.
4, and the last one
And
is
the
worth
8.
8, right? So this is the first time we're using the A or the 8, because before we just counted till 7. We didn't need it. Now this is Q4. Sam, what that means is, based on what I have here, Sam, at several spots, this is my reset circuit. This is telling me, well, your NAND gate, you have to basically tap off of Q4 and Q2. Guys, this is pivotal information. You have to be listening. Q4, where is Q4? Well, Q4 is right here. Okay? So this is Q4 right here. And Q2 is?
Q4.
Q2 is right here. Do you understand why I'm tapping off of there? Because I have a reset circuit that tells me in order for me to restart counting at 10, I have to use a NAND gate, and the two inputs of the NAND gates are going to go to Q4 and Q2. So that's what I'm showing here. I'm tapping off of a counter. Without this reset circuit, this would count from 0, 0, 0, 0 to 1, 1, 1, 1, which basically is 0 to 15. But now that I'm taking the Q4 and Q2 going into this guy here, which is an AND, which is a 0, who remembers what this was? A NAND gate.
08.
No. A 0, 2. And from here, the output, I'm going to go to clear, jump into clear,
And
jump into clear, jump into clear.
okay.
Okay, that means you understand. I don't have to explain anymore. Everything's good.
It's good. And please show all the diagram. Yes, I can.
Just 1 second, just 1 second. You're too fast. Look here, we're gonna start again with our diagram. Please pay attention. This is pivotal information, crucial. At 8, we have 1, 0, 0, 0. At 8, we have 1, 0, 0, 0. Okay, that's the value of the bits. But remember that when this is a 1, what do I have on my 7-segment display?
8.
8.
Yeah.
I'm just trying to. So I have an 8. Okay. I'll just draw it here. It's a little tight on that side, but I have an 8. Okay. What's going to happen at the next clock pulse? I'm going to go to 9. Okay. Before I show you 9, let me just show you that this guy here is a 1. Q2 here is a 0.
0.
0 and 1, the output of an AND gate is 0. Inverted is a 1. What does 1 mean? 1 represents 5 volts. So if I have full 5 volts on clear, am I resetting the clears?
No reset.
No, I reset with 0 volts or logical 0. As long as this is 1, I am not resetting, it's just counting. So now I said the next number was 9. So I'm going to erase this guy here. It just counted to 9. So remember 1001 is 9. Did it change the value of Q2?
No change.
No change. So it's gonna display a 9. I have a 9. The next count after 9 is 10, which is 1010. So 1010. So the numbers will change. These two will change. It just incremented by 1. So this is now a 1. This is now 0. So now what's going to happen? This guy here, Q2, is a 1. Let me get rid of this. Let me get rid of this. Let me get rid of this. And these guys here as well. And take it one step at a time. So now, my Q4 here is a 1. My Q2 here, Sardi, is a 1. Sardi, 1 and a 1, the output of an AND would be?
1.
1. Inverted is a 0.
0.
If I have a 0 on my clears, what's going to happen?
It clears with a 0.
Clear.
It clears. Am I going to see a 10? No, this is
No.
going to be, this is
It's
going to go
0.
straight to 0. This is going to go straight to 0. And the other ones are already 0. So
Yeah.
now I'm going to go from 9 to 0. That is what the reset circuit does. Is it understandable? Is it palatable?
Yes. Hold on.
Hold on. We take a picture.
Capture the
Do you
capture
want to
the
picture
screen.
me as well, or just that?
Yes, handsome. I show my family you're handsome.
But now that's the whole thing. There's nothing else after that. That's what we're building, the counter.
Every mod is going to be a different reset circuit, but ultimately, yes, this is the principle behind it. Yes.
Beautiful.
Class, the one you want us to build in class, I guess, is we're going to do the mod 10. We're not going to.
You have a lot of them. You have a lot of them to build in class. Okay,
No,
but
we're
this
gonna
is
build up to the mod 10, right? We're going to start off with the mod for the little ones, and then we're going to go up, right?
not necessarily. We can start with a mod 10 and then choose other ones. Okay, so I'm going to go through it one more time for just in case you did not understand. So again, we want a mod 10. We need 4 bits. When we have 4 bits, naturally, we're going to count from 0000 to 1111, which gives me 15, but I want to stop at 10. So I put a 1 in the truth table. I take the values of the reset here, and I plug them into Karnaugh. I simplify. I want to get rid of the 1 with the help of the x's. I don't care of whatever x that can't go into my group. I simplify, I get Q4, Q2. What that means is I'm going to take Q4 and Q2, build a reset circuit with a NAND gate that will be attached to my counter. So my counter is made up of JKs all the time. Well, in this course anyway. There are other ways of doing it. Okay, so I have this, which you have to know how to build and write, and actually you have to know all the pin numbers as well. So I take this, which without a reset circuit will count from 0000 to 1111. So it will continue to count after 9, it will continue to count to 15. But I'm putting in a reset circuit, and I just showed you what happens with the reset circuit. It resets after 9 and goes back to 0.
The clears, they're wired in